Welcome back to the TURBO9 project. In this video, we're going to give an update on our master's thesis. This is our master's thesis research summer update covering verification and design.
So we have 4 excellent faculty members from the University of Florida Electrical and Computer Engineering Department on our supervisory committee. We have Dr. Greg Stitt as our chair, along with Dr. Herman Lamb, Dr. William Eisenstadt, and Dr. Eric M. Schwartz. My name is Kevin Phillipson. My project responsibilities are the microarchitecture design, the RTL development, microcode development, and I have 13 years of industry experience in ASIC design. I have a bachelor's in electrical engineering from the University of Florida, and my master's thesis is the development, analysis, and optimization of a compact and efficient microprocessor IP.
And I'm Michael Rywalt. My project responsibilities are custom microcode macro assembler, C compiler support, and verification. I also have 13 years of industry experience in ASIC design, and I hold a bachelor's of science in computer science and software engineering from the Florida Institute of Technology. And my master's thesis is verification of a compact and efficient microprocessor IP. So first we'll do a quick overview of the project, look at some of the previous work that was done, and then we'll move on to the verification test bench and give a pretty in-depth overview, which was the majority of the work this semester. It was an all hands-on-deck effort between both Kevin and I. And then we'll go through design status and give some quick review updates on that. And we'll look at the toolkit, and we'll give a demo of the test bench and the toolkit. Then we'll go over next steps for our master's theses, and then we'll give some acknowledgments at the end.
Okay, I'm going to give a quick overview here of our previous work. There is a video that goes into all this in detail, so if you haven't watched that, please go back and watch that to fill in any details I'm going to gloss over. But just to get everyone on the same page, I'm going to go over this quickly. So the goal of our project is to design an open source professional level microprocessor IP, similar to the, say the RISC-V or ARM level. Now we're not going to try to build a 32-bit or 64-bit architecture to compete with RISC-V or ARM. Instead, we're going to target an 8 or 16-bit architecture targeted for SoC subblocks or small ASICs, where you need high-level reprogrammable control, or maybe you need a design for test, or you need to manage a command interface or such. And what do we mean by professional level IP? Well, first, you have to have third-party support. So we're going to look for an architecture that already has assemblers, compilers, and an existing code base. And we're going to use modern RTL design techniques and good practice. We're going to use a standard SoC bus. In this case, we'll be using the pipeline Wishbone bus. And then we're going to take the extra step of optimizing our design for speed, power, and area. We're not going to just try to get something working, but we're also going to try to make it as small and as efficient as possible. And lastly, which is probably the most important aspect of professional IP, is we're going to build a complete verification test bench that goes through every single instruction and test the entire instruction set. So we chose the 6009 instruction set, long story short. And why do we choose this? Well, we're looking for something that is going to produce compact code. And so the 6009 is a very elegant instruction set. It is CISC. It's not exactly a very large CISC processor. It's more of an accumulator type of architecture. So that's going to be a little more challenging to pipeline, but I think that's going to make things interesting too. And we chose the pipeline Wishbone bus because we want to keep that bus busy. Our memory bus, we want to have something happening on every single clock cycle, and not just that. When you have a pipelined bus fabric, then you can actually reduce some of your propagation delays in your memory bus, which oftentimes becomes the worst timing path. So that gives us the most efficient bus architecture in our opinion. So in order to have a pipelined bus, we also need to have a pipelined microarchitecture. So the internal of the microprocessor is going to be pipelined as well. So to give you an idea of what the TURBO9 looks like at a high level, we have a fetch stage, a decode stage, and an execute stage. And the execute stage has its own data bus for data, and then the fetch stage has a program data bus, like a Harvard architecture. But externally, the TURBO9 is von Neumann. So we have a Wishbone controller, which converts the Harvard architecture to a von Neumann architecture outside of the IP. And then outside the IP, you can have as many pipeline registers as you need to meet timing. And the Wishbone controller here actually will adjust for it automatically. In this case, the way I have it drawn, we have 6 pipeline stages: 1, 2, 3, 4, 5, 6. Here's a detailed look at the microarchitecture. This is the fetch stage. It has a 8-byte FIFO. There's obviously some logic here to control the pending transaction and flush logic. We won't go into too much detail. Then we have a decode stage. So the decode stage has a lot of logic just to decode the instruction, figure out how long the instruction is, and figure out what registers are going to be used. And that feeds into a microsequencer that, combined with those decode tables, creates a micro-op. This is similar to how many pipeline CISC architectures work. They take the complex CISC instructions and they convert them into micro-ops, which are like RISC instructions essentially. And then we have a execute stage. It has a register file. It has 2 ALUs, 16-bit ALUs, and a data memory controller. And this data memory controller can actually act as another pipeline stage in some cases. If you're doing a 16-bit write, it'll actually allow the rest of the pipeline to continue, and it'll implement the extra cycles to do a 16-bit write. The execute stage can also be multi-cycle. If the instruction requires it, you can feed multiple micro-ops into the execute stage as necessary. Now, just to go over one of the unique aspects of our architecture, which is the custom microcode assembler. So this is something that Michael developed. And so what it does is we developed our own microcode, which is kind of like our own language, to build our state machine, our sequencer. So that basically takes this microcode and it will assemble it into what ends up being actually Verilog, and that Verilog can be synthesized into gates, or you can create a memory with it. A lot of people get hung up on whether you have a random logic derived sequencer, or you have a microprogram ROM. In our case, we can do either. When you really understand what's going on, a sequencer is a sequencer. We're using a microcode assembler because it gives us a much more structured way to build our sequencer and build our control unit. And it also gives us some other features which are very useful. Here's a quick example of the microcode. It's a macro assembler. So here's the microcode itself, and each one of these are macros, which are defined in a macro file, which allows us to be very flexible. So as the microarchitecture changes, we can change the macros to fit the microarchitecture. This is the Verilog output. And these are the decode tables. So in addition to the microcode, it also creates other Verilog files which are used in parallel to the microcode file. So like when you have a microprogram ROM, that would usually go through several sequences in order to execute an instruction. We actually added it so that you can, we're actually outputting 16 different Verilog files, and some of them are used to decode directly off the instruction so that we can compress our microstates down, microcycles. So these decode tables are actually are derived from the microcode itself, and they go into separate files that are essentially lookup tables to specify which register, the starting address in the microcode, and whatnot. And then one of the great things about our microcode assembler is it actually produces statistics on the control vectors. And so one thing when you're writing a big state machine or a big sequencer, you have to understand how often you're using some control vector and how you've encoded it. So we have pretty much the entire instruction set now in microcode, and the statistics have been very useful at this point because I can go and look at how certain control vectors are being encoded, and I can make design choices in the microarchitecture based on those statistics. Without this, I would be blind to a lot of stuff in the design process. We also analyze the clock for clock performance. Now, in order to compare apples to apples, the 6809 has a bus cycle that is 4 clock cycles, and that's usually referred to as the E clock. The TURBO9 has a bus cycle of 1 clock. So we're going to compare clock for clock here to keep things even. And so we went through a bunch of different instructions. The inherit instructions we were getting about eight times. These are just various instructions, but you can see 7, 6. The jump instruction, there's no branch prediction here, and it was misinterpreting the jump in this case. Branch prediction is something that we're looking to implement though. And then overall, we looked at a test case and came up with a 5.2 times faster clock for clock. So keep in mind, you can implement the TURBO9 on a newer technology and run probably in the gigahertz. But if you were to run it at the same speed as a 6809, it would be 5.2 times faster given the same clock. And we've been using a Xilinx RTX 7 FPGA, and we're still meeting timing at 100 megahertz. We haven't optimized anything yet, but it's a good baseline to keep synthesizing, just to make sure that I'm not creating any extremely long timing paths.
Let's look at the IP design and verification flow. For both verification and design, we begin with a specification. It's a document that describes what's being designed, and using that, we'll come up with a verification strategy, how we're going to verify this design. And then from that document, we can start to collect attributes, and I'll discuss what attributes are coming up. But from the attributes list, you can begin to develop test cases, what you're actually going to be testing. And then once you have a collection of these test cases, you can build a regression that runs nightly with randomization. And then when the regression is complete with a certain percentage of the test cases or all the test cases, you can start looking at coverage and see where you're starting to kind of falter in what you're covering in the design. You can look at things like toggle, block, or expression coverage in there. And then you can start to move on to release IP. But the test regression suite is used by design as well to debug some of their failures as they develop.
Yeah, so from the design side, obviously we also start with the design specification. And we look at in this case, the instruction set and try to decide what blocks we need from a high level and lay that out. And then from the high level architecture design, we move into microarchitecture design. So we look at those individual blocks and start to make a best guess on what we're going to need to put inside those blocks. And then we start to actually code that up in Verilog, RTL, and microcode. Then once we have something running, we can start running tests. Now this could be a simple stimulation test, or if Mike has something more advanced ready, we can actually start to verify our instructions. And then as we find bugs, we move back into the microarchitecture stage and make adjustments and recode them in Verilog or microcode, and then retest. Once we start to get passing tests, then we can move into the synthesis stage and start looking at area and timing paths and power, and start to optimize those. And that would feed back into our microarchitecture, those adjustments, which would then obviously be recoded and retested. And then once we're happy with our synthesis, we can release IP.
And now we'll have to ask ourselves, what are we verifying? Well, we're verifying an instruction set architecture. So we're going to be leaving the microarchitecture itself as like a black box. Each instruction will take an input, produce an output, and we're going to figure out if that output is correct or not. So we'll be verifying the behavior of the ISA, and we'll be ignoring the cycle timing of the original design, but we'll be measuring our own cycle timing as a necessary step to optimize our design.
So the next question is, how do you test a instruction? So if we think of a instruction as a black box, in this case we're doing a add a, what are the inputs and outputs? So the inputs and outputs are the current state of the processor, which comes down to its programming model or its internal registers. The values in that affect the instruction, and the memory as well. So in a lot of instructions also read memory, so those can contain inputs and outputs as well. So now that leads us to the question, how do we write these inputs and outputs from the test bench?
So how do we initialize the processor state? Well, let's look at a very simple code example here to understand how that works. So the first thing we do is we use the pull instruction to pull all the registers off the stack into the processor. And before we do that, the test bench is actually going to overwrite all of these values here that get pulled using the pull instruction above. And then we move on to the code under test. And the test bench will have replaced the add a instruction with whatever instruction it is that's under test at that moment. And then when we finish running that instruction, we'll jump to our done state, if you will. And at that point, we've encapsulated all of our inputs and outputs into just a single memory.
Okay, so let's take a more in-depth look at the memory that we have to build for each test. So we start with a template. So this is the test bench program template. It's still a little bit simplified, but this will get the point across. So the first thing to note here is that we have a code block, and we have a data block, and we have a stack area, and we have a reset vector area. And then we have some code that's used to get in and out of this test. The first thing the test bench does is it actually inserts random data. It overwrites the code block, the data block, and the stack block, and the reset area, and then it comes back and it writes the actual directed data in place. So it will then write the machine code for the corresponding opcode, and it'll write the necessary registers to set up the test correctly. Okay, now that we got that out of the way, let's look at how this program works. So when the program starts, it sets the least significant bit on the output port to signal done to the test bench. So now the test bench knows that the program is running. And then, like we talked about before, it pulls the entire processor state off the stack. This includes the program counter. Now the program counter will be set to the code under test address, so it'll actually jump down here, and then it'll execute that opcode that the test bench wrote in there. It could be multiple opcodes depending on how complex the test case is. And then we jump back here to the done label, and on the done label we actually push the entire processor state back onto the stack. Now why do we do this? Well, because we need to know what the state was after the instruction. So that'll push all the registers back onto the stack, and then we set the most significant bit of the output port to signal back to the test bench that we are complete. And then we just enter an infinite loop and wait for the test bench to reset the processor.
So let's look at the verification test bench at the top level here. So the top of the screen here, we have our test bench, and inside of that we have our instruction test case. This is our behavioral Verilog that we're building up here. We'll create the memory here that we'll pass down, and we'll execute on the TURBO9, but we also have to execute it on something that behaves like the TURBO9. So what we've created is a behavioral model of the 6809 written in Verilog, and yes, it's another 6809, and we'll use this to compare it to the results that we get back from the TURBO9. So we pass memories down to both of them. They both execute the instructions. We'll get the same start and done signals from both the TURBO9 and the model. And when the test case detects that everything is finished, it'll get the memory back from both, do a comparison between the two, And if they're the same, if there's no differences, then we consider that a pass. And if there's any difference, then we consider that a failure, at which time we can go back in and debug what's happened.
Okay, so let's take a look at what each test case is doing. The first thing we do is we load that test bench template, right? So we have it assembled, pre-assembled, and then we load this template into the test bench. And we randomize all the code, data, stack, and the vector blocks. And then we write the opcode or opcodes under test. So the test bench is actually writing machine code. It's actually writing machine code directly into this memory image. And then we select an effective address for that particular instruction. So wherever that instruction is going to access memory, we select a random effective address, and then we back calculate whatever the addressing mode is. We back calculate what the registers need to be to point to that effective address. And we initialize those registers on the stack. Now we're done. Now we have a memory image that we can copy into the TURBO9 and the 6809 behavioral model. And so in the previous slide, Mike was talking about behavioral Verilog and RTL Verilog. So there's behavioral Verilog, which acts like C. That is our behavioral model and our test bench. And then we have RTL, which is a subset of Verilog that can be synthesized. So we copy this memory image into both of those processors. And then we reset both of them, and we wait for the start and done signals. And then we compare the memory from the TURBO9 and the 6809 model. And if they match, that's a pass. If they fail, then we know that we have a problem, and we flag that. And then the other thing that we do is that we go through random iterations. So one instruction, we can set how many random iterations we want to do. So we can loop for 1,000 random iterations and just randomize the anything that's not a directed input. And then oftentimes the test case will have multiple instructions, like instructions that have the same addressing mode. And so there's a for loop to go to the next instruction or go to the next random iteration. And so that's basically how each test case works.
Okay, so let's look at another step in the verification methodology, which is attributes collection. I think first we should probably define what an attribute is in the context of design verification. An attribute is an atomic feature or component of the given device under test that shall be tested. In our case, because we're using an ISA as our specification, the most atomic components we have are the instructions themselves, the registers, and the memories. A test case can cover multiple attributes. You can have multiple instructions in any of the test cases. And in our case, each instruction, but its addressing mode, which is equally important, as it's a variation of each instruction tested, counts as an attribute.
Let's take a look at the instruction set of the 6809. So its instructions have a granularity of 8 bits, and they can be variable length. So this is the first page of possible instructions. And one thing to note here is, like Mike was saying, one instruction can have multiple addressing modes. So if we were to look, for example, here at a subtract A, it can have an immediate addressing mode, a direct addressing mode, an index addressing mode, and then an extended addressing mode. Now, the index addressing mode on the 6809 is very powerful. So what happens there is there's a post byte, and the post byte can then encode several different versions of indexed addressing. So every single one of those variations then multiplies out the number of attributes for that one instruction. So just take a look at the rest of the opcode matrix here, page 2. The gray are unimplemented opcodes. Then here's the matrix for the post byte. So you can see that this is all the different indexing addressing modes and how they're encoded in that post byte. So if you were to look at this and break down all the different possible addressing modes, and then also add in some exceptions such as jump instructions, branch instructions, which require a special way to test them, stack instructions, software interrupts, and hardware interrupts, we've come up with a possible variations of instructions of 4,748, and then plus 4 hardware interrupts. We're looking at 4,572 total attributes. Of these, we believe that we can group them into 28 separate test cases.
So let's take a look at a snapshot of instruction tests that have been implemented so far. If you look at the overall tests implemented up top on the left here, it looks like we've done 36.5% so far. We worked very hard to get to this point. And all of these pie charts are derived from the attributes list, so we can get a better idea of where we are doing the best. Right now, we've implemented 97% of the relative tests, 96% of the extended, and then we go back down to immediate, and then inherent, and then indexed. Index suffers a little bit, but that's only because it's broken down into mode types, variations, and direct and indirect types of tests. All right, so let's take a look at the current verification status. What we completed so far, of course, is the top level test bench. We have our building block functions in our test bench library, which allow us to write machine code to memory. We have our top level DUT wrapper, which instantiates the design and the behavioral model. We have our test case program, which we described before, which is what we're using those building block functions to write into. We have our debug run scripts and a full nightly regression that runs all of our tests that we have so far once a night around 5 a.m. In progress, we have the behavioral model, which has remaining instructions to be implemented, and then all of the rest of the test cases for the attributes that are still uncovered. And then we'd like to move on to benchmark programs like Drystone, which is a compiler-dependent benchmark. So it'll be developed in a C language, and then whatever the compiler outputs as assembly is what we get. But then we can also do assembly mode benchmark programs, which are hand optimized. And these can be used as a metric for optimizing the microarchitecture down the road.
Okay, so just to give a quick update on the design. So like we said earlier, most of my work this semester was involved in building the test bench, so I was heavily involved in that as well. And then I had to come back to the design in order to make the two work together. One of the major things that we did is that we converted everything from System Verilog to Verilog 2001, and I'll explain why later. And then we did a major hierarchy cleanup. So as this microarchitecture is drawn, in reality, when we left it last time, this pipeline register was kind of broken up in different parts of the hierarchy. So I took all of the hierarchy associated with the controller and I moved it back into the decode stage, and then I created the pipeline register all in one spot. And the other major thing that needed to be done was I had to pull all of the index addressing mode control into one place, because we had to add the stack instruction hardware, which is actually very similar to the index addressing mode hardware. So I pulled logic from the address ALU and from the instruction decode logic, and I put it all into a new block called the address and address control, which used to be the register pointer logic. So by putting all this common logic in one spot, I was able to optimize it. And then I added the stack hardware control, so there's logic in there to help the microsequencer control this block to then do the stack instructions like push, pull, return, and jump to subroutine. Okay, so to give a current status of where we are, at this point the microarchitecture is pretty mature, and the microcode is also mature. We pretty much got all the instructions implemented. We are missing the multiply instruction, and the reason we're missing that is because we're going to have to do some hardware modifications to the data ALU for the shift and add algorithm. So I haven't done that yet, and I need to add the hardware interrupts, and then the big effort is going to be to start to run all these through Mike's test cases and debug any errors. So every night there'll be a regression run, and that's going to run through all the current test cases, and I can go in there and look at what's failing and correct those errors. With either they're going to be errors that are in the actually true errors that are in the microarchitecture, or they're going to be errors in the test case or the behavioral model. So we have to decide where that error is and fix it.
All right, so let's look at the toolkit that we put together this semester. When we approached this project this semester, we kind of began to realize that if we're going to continue doing this project going forward, or as this gets out into the open as an open source project, using Cadence tools, which we started on, really limits us to just being able to do things using the licenses that cost hundreds of thousands of dollars and that are provided by the school. Open source is really open for everyone, so our decision was to move to open source tools. And that using those, we can go on in the future, continue developing our project.
Yeah, so we needed a Verilog simulator, and I mentioned earlier that we had to convert everything from System Verilog into Verilog 2001. And the main reason we did this is because we started using Icarus Verilog, which is the open source Verilog 2001 simulator. It does have some System Verilog support, but it's not complete yet. And we figured it's best to just do system to use Verilog 2001, because not only for Icarus Verilog, but there's actually a lot of other tools out there which only support Verilog 2001. So everything that we've built now, all of our run and regression scripts are built around Verilog.
We also use our own microcode assembler, which is, of course, open source. It's the macro-based custom assembler that we've talked about several of our videos in the past.
Yeah, Mike did a really good job of that. I really enjoy using it.
Thank you.
And then for wave viewing, we used GTK Wave, which is basically can be used to view the VCD files that are produced by Verilog. And for right now, we're using Xilinx tools for FPGA synthesis. Our IP is target independent, but for right now, this is the synthesis tool that we're using. And then we're using the LW Tools 6809 assembler, excellent assembler. I actually donated to this project, and we will be using various C compiler. There's a GCC version, and then there's also other compilers, CMOC, DCC, and microC. Okay, now we're going to give a demonstration of the TURBO9 development toolkit. To show this, I'm going to show some simulation, and then I'm going to break the design in various ways and show how the simulation is affected. Okay, so what we have here is our Linux box with our toolkit installed. First thing I'm going to do is go ahead and run a simulation. We use our C shell script that we use to run all of our tests, and basically this is going to load the top level test bench. We're going to do a reduced set of the direct instructions. So for our purposes, this is just going to be a smaller subset. We're going to do 5 iterations, and we're going to dump waves, and then this is just setting it's forcing the seed for the randomization. Okay, so we get a pass. Let's go ahead and just look at waves really quick. Let's just show you that. This is GTK wave. This is our waveform viewer, and we're going to load the VCD file. Okay. This gives us our hierarchy over here, and we're going to go down into the SoC into the TURBO9. The first thing I usually do is grab the program counter, and that's done in the register array. And here it is. there's the program counter. And grab the clock. It's always a good thing. And get that output port that has the start and done signals to the test bench. While we're here, let's also get the 6009 behavioral model, get its program counter, and its output port. Okay, now let's just zoom back until we get something interesting. Okay. Let's see, the first thing to notice is, let's look at the program counter. So you can see here that the TURBO9 program counter is actually a lot shorter than the 6009 model. So you can see here that this particular instruction is taking this amount of time, sorry. This instruction is taking this amount of time, and the instructions are on the TURBO9 are typically a lot less. In fact, this one here is only one cycle. And then we can also see that on the time between the start bit. So here's the output port, here's the start bit, and here's the done bit. And then for the that's this is for the TURBO9, and then this is for versus this is the amount of time it takes for the 6809. So obviously this is a way that we can debug certain things, but most of the time the first thing that we look at is the summary log. So this is the summary log from the test bench. And so if you look on the left here, you can see what level of the test bench is outputting to the log. So in this case, this is the top level. And then here is the actual test case level, and it's reporting what instructions it's testing. In this case, this must be 11 instructions because there's 5 iterations for each instruction, and there's 55 passing tests. So this is just the summary log. This is the detailed log. So here we're testing the negate instruction. So we kind of went over this earlier. It's loading the test bench template file, and then it's writing random data in the data blocks. It's writing the machine code for the opcode under test. It's writing a jump instruction back to the done section of the code, so on and so forth. What else is interesting here? It's resetting the device under test and the model. And then you can actually see the model is actually able to, since it's a behavioral model, it can communicate out to the log as well, and it can tell you what instructions it's executing and what address those are at. Here's the output port, so it's waiting for the bits to be set, the start and the end. And then at the very end here, you can see that we're comparing the device under test memory and the model memory. And in this case, they match, and therefore this test passed. Well, that's cool. Let's break something. So okay, so this is the negate instruction, right? So what that does is it changes the sign of the operand. So let's see if we can break that. Let's break that in microcode first. Find our microcode. Here we go. All right, so our negate instruction is here in microcode. So we are doing the direct version of the negate instruction. There's also index, extended, and the A and the B register. And anyway, so we're doing the direct, which operates on the data memory. So this is the opcode is 0, and the register pointer are pointing to data memory. So in order to do a negate, you're essentially changing the sign of the operand. And so this is the macro that gets assembled into the micro op for the data ALU. And in this case, we're doing a subtract. So we're subtracting a constant of 0. We're subtracting the operand from a constant of 0. So 0 minus something is going to flip the sign, right? So if you have a negative number, if you have a positive number and you subtract it from 0, you're going to get a negative number. If you have a negative number and you subtract a negative from 0, then you're going to get a positive number. So let's break this. Simple way to break this would be do an add instead, correct? So go to our microcode assembler and we'll make the microcode, and it made successfully. And let's go ahead and rerun. I don't want to dump waves. This will run faster without that dump. We failed. Okay, so let's go look at our log and see how we failed. See if that Testbench knows what's going on. So let's go back. So the summary is we're now failing for the negate instruction. Well, that's good. So far it makes sense. I lost my other run log. I apologize. There it is. Okay. So let's take a look and see what's happening. So it seems to run fine. But we get an error on the memory mismatch. So what's mismatching here? So what address is this? Where is this? How I usually figure this out is I go to FFE4. So let's go look at the listing file. This is the listing file for our template. And FFE4 is right here, which is the condition code register. Now, why would that fail? Okay, so we're doing a negate, right? So the condition code register has a sign bit in it. So obviously the sign bit is incorrect. And that's why when the processor dumped its state back out onto the stack, it put the condition code register here, and one of the bits was incorrect. And that's why it failed. Or it could be multiple bits because it could also affect the carry. And now let's look at this other address. So what is this? Okay, so this must be the data, the operand. Yes, it is. Okay, so here's the effective address of the instruction. So this is where the data it operated on, and so it's telling me that that's incorrect too. Okay, let's fix our processor. I don't like having broken things, so let's go ahead and fix it. Go back to subtract and rerun this. Okay. And then rerun our simulation. Yes, we got a pass. Good. Now, let's break it in another way. Let's break it in the RTL. We've got some RTL up here. The data ALU. Okay. So this is the data ALU, and we're doing a partial decode here of the A plus B. So the functions of the data ALU. So you can do A plus B, A plus not B, and that is essentially the subtract. And you do shifts, adds, and or an XOR. But here is the partial decode for this. So the reason we use partial decoding is for speed. But this is essentially the subtract, and I am inverting the B side and inverting the carry. That's the kind of how you do the two's complement inversion. How you flip the sign on a two's complement number. Let's just take the inversion out of one, and let's see if we broke something again. Yes, we broke something. Go ahead and take a look. Here's the detail log. Okay, so yep, there's our CCR, and then this is the effective address. Yeah, so we broke that. correctly. Let's fix it. I don't like breaking things. I need to show the fast. Okay. I want to show the statistics from the microcode assembler to get an idea of how that works. So let me get an example here. Since we've been using the data ALU, let's look at that again. That's a good. Okay, so these are all the control vectors. So if you look at the micro operation, you have all these control vectors that go over to your data path or your execute stage. And so like I was saying before, this is A plus B, this is A plus not B, left shift, right shift, and or XOR. And you can see that XOR is only used one time because it's only used for the XOR instruction. But the add is used a lot because it's used not only for adding, but also for just passing. If you just want to pass data through, you usually just do an add with 0. So anyway, so that gives me an idea of how many times we're using this in the microcode. So we have the full instruction set implemented, right? And looking at this, it gives me the statistics on how often I use each one of these. And then we also have these. It also does the decode table. Let me find an interesting example for that. So these are the register pointers. So these. So the reason we use register pointers, if you look back at the microcode, I'll just jump back quickly. You'll see in this example, this is the negate, the instruction for the negate, sorry, the microcode for the negate instruction. But each one of these numbers is one opcode. So we're using the same microcode for, let's see, 1, 2, 3, 4, 5 different opcodes. And what we're doing is we're just changing the register pointers. So the register pointer in this case is A, the register pointer points to B in this case, and then data memory for these cases. And then these are the jump tables. So these will do different addressing modes. So this is jump table A. It comes directly here because there is no addressing mode. This is an inherent instruction. This is jump table B. So it is, if we come back, we'll see a direct addressing mode microcode here. So we go back. Should see, okay, so here's the index addressing mode microcode. Here's the direct and extended. So these are all, so this is the addressing mode microcode, and we can see that all these use the same piece of microcode where they pass the immediate data, which can be direct or extended depending on the hardware, into the effective address. Then it does a data memory load. The address is the direct or extended address, and then it goes jump table B, which then takes you down to the rest of the microcode. Anyway, I'm getting sidetracked here, but just to wrap this up. So this is the address pointer for the A side of the data ALU, and you can see I use all the registers on this side, or most of them on this side are decoded out and out of the decode tables. Then for the B side, I don't use all the registers. And so why is this important? Well, if I'm writing microcode and I need to grab one of these registers for an ALU function, I obviously don't want to use this side unless I have to, because I don't want to add another use on this side, because I can actually reduce the size of the mux on this side. So there's a mux that takes all these registers into that side of the data ALU. So if I can reduce the size of the mux and reduce area. So knowing that information is important, and that's a simple example, but there's other reasons. But I mean, this gives me great insight into once you have all your microcode for your entire instruction set, I can make decisions on how to optimize the microarchitecture. So I'm not aware of any other microassembler that does this. This is something that Mike and I came up with, and it's extremely useful. Anyway, I think that's a good overview. Okay, so let's talk about the next steps for our theses. So we need to get to a baseline. So we need to complete the processor and the test bench. And by this, we mean unoptimized. And the reason is because if we start to go into an optimization process, we have to have a known stopping point. We need to have a full instruction set. Like if I was to try to optimize the processor and haven't added the multiply instruction yet, that would affect my area, power, and for frequency numbers, right? So we need to get the processor and the test bench to the state where we have implemented everything. And then for the master's theses, we need to start quantifying data. Some of this I've already done. I've already kept track of how the area has grown as I've implemented certain instructions. But I need to get my hands on a standard logic library synthesis tool and start looking at the benchmark numbers as well and optimize for area, power, and performance. So we can look at the area from the number of gates from the synthesis tool. We can look at the power by using a FPGA and a current meter. And the performance would be a combination of looking at the cycle-by-cycle performance and the absolute Fmax, the fastest clock rate. And then I want to also evaluate certain improvements such as branch prediction, stall logic, and looking at the microcode statistics and seeing if we can make any improvements there.
On my side, I'll continue looking at the analysis of test coverage. By doing this, I'll have to use Cadence IMC tool, and that's not an open source tool. So we've talked about making this project open source, but we'll have to revert to this closed source tool because there doesn't appear to be an equivalent in the open source community. But that's fine, as we're in an academic institution at the time that's helping us out in being able to perform these tests and analyses. And then I'll continue to look at the attributes versus lead toggle and other metrics that come out of IMC and see where we can start to develop other tests. Maybe randomization is not enough. We might need to develop more directed tests to cover different parts of the design.
Yeah, and also note, I mean, so I will probably be using a non-open source tool for the standard logic library synthesis. But what we mean is with open source is that once we put this out, all of our test bench and our core can be run with all of the Go scripts will be based on a open source toolkit. Okay, so there's some people that we would like to acknowledge. The first is the late Dr. Lynch. He was a faculty member in the electrical engineering department at UF. And he was the author of Microprogram State Machine Design, and he was my teacher for digital design and computer architecture. And he's responsible for lighting that initial spark that got me interested in digital design and my future career and processor design, and indirectly has also influenced Mike.
Yes, and we'd also like to acknowledge Terry Ritter and the late Joel Boney, who were the co-architects of the original 6809 processor. They used analysis of 6800 code to design the elegant 6809 ISA and wrote the specification that we're using today to develop the TURBO9. We're also keeping Terry up to date on some of the work that we're doing. We're keeping in contact with him.
And one of the surprises actually is we've been embraced by the Tandy color computer community, which is a group of retro computer enthusiasts, and obviously the Tandy color computer uses the 6809 processor, but they've been great because they've preserved a lot of the 6809 documentation that we use. In addition to that, they continue to actually develop 6809 tools. They have new compilers and new assemblers and all kinds of stuff coming out, and not just tools. I mean, there's a huge 6809 software base out there that they're maintaining and developing. A couple of the interesting ones that to mention here is OS9 and Fuzzix, which are Unix-like multi-user operating systems. So that's been a really a great help and a great resource for us.
And that about wraps it up. Thanks for watching.